In this video, we're going to finish off section 2.3 on the relative position of lines and planes by doing example 2.3.3 and then by filling in a flowchart about the procedure that we use to distinguish between the relationship of these two planes. So let's start by reviewing what we'd seen in the previous video, the three possibilities for the relative position of two planes. They can be parallel, two planes can be coincident, or they can be intersecting at a line. And one of those cases immediately becomes clear if you examine the normal vectors. So n1 is not parallel to n2 in the case where the two planes are intersecting at a line. In the case where the two planes are parallel or coincident, the normal vectors are parallel to each other, and you have to examine the full plane equations. In the case where the planes are parallel, the equations are not multiples of each other, whereas in the case that the planes are coincident, the plane equations are multiples of each other. So we are going to start, first of all, by examining the normal vector. And then if we need to, we'll do a follow-up examination of the plane equations. So let's go do here example 2.3.3. Determine the relationship between the planes pi 1 minus 2x plus y minus 6z equals 4 and pi 2 x minus 1/2 y plus 3z plus 2 equals 0. So let's look at the normal vectors. N1, remember we're reading the coefficients of the x, y, z. So minus 2, 1, minus 6. And N2 is 1, minus 1/2, 3. And we want to know if these are parallel, and so we want to know if they are multiples. And a quick inspection of these gives us that we can multiply n1 by minus 1/2, so n2 is minus 1/2 times n1, which means that n2 and n1 are indeed parallel. So our planes are either coincident or parallel. So to distinguish between those cases, we're going to examine the full equations. So pi 1's equation, now I'm going to move everything over to one side so that the equations match completely in form. So minus 2x plus y minus 6z, bring them 4 over, so minus 4 equals 0. Pi 2's equation, I'll just recopy, x minus 1/2 y plus 3z plus 2 equals 0. So we know that the normal vector, in other words the coefficients, the first three coefficients, well the coefficients of x, y, and z are going to be multiples, the same multiples of each other. We identified that multiple as minus 1/2. What we want to know now is, does the constant, does the d also share that relationship? And in fact it does. If we multiply the equation here, the full equation, by minus 1/2, so we're saying that d2 is minus 1/2, the same multiple that we had for the normal vectors, times d1, in other words 2 is minus 1/2 times minus 4, that the full equations are multiples of each other, and therefore that is telling us that the planes are coincident. So let's go through and fill out the flow chart that captures this procedure. So the decision tree for two planes, the first thing we did is to examine the normal vector. Is n1 parallel to n2? And we answered yes, which means that the planes were either coincident or parallel, as in the images that you can see down at the bottom of your screen. If we had answered no to this, well, that one situation where the normal vectors are not Parallel is when the planes are intersecting at a line. To distinguish between the coincident and parallel cases, we asked a follow-up question. Are the plane equations multiples of each other? We indeed answered yes, and that was because our planes were coincident. But if we had answered no, we would have been in the remaining case where the planes were parallel.